enjoyed your break. Um, at this point, you've got about 5 weeks, then Easter break, and then about 5 weeks, and then finals. So
I thought there's only 9 weeks left.
Easter break? No, wait. We've got. Wait, how many?
there's 10 weeks left in school.
So 50 days.
What?
What?
What do you
Yeah,
mean?
10
yeah.
times 5,
You
5
can't make
days.
half
Like
days.
school,
Where are you getting
school
10?
days. 50
Were you getting
days.
10?
About.
Where are you getting 10?
There's 10 weeks left.
Wait, how long is Easter break? Did you count
There's
Easter break?
7.
Okay.
There's 7
All right.
days.
Stop.
Mr. Davis.
Give it a rest, guys. No, I'm not answering any questions. Okay. So I just am saying that's about how much time you have in round figures. I'm not going to figure out how many days, nor do I care how many days there are, nor do I think you should count down the days. When you start counting down the days, then you don't live the days that you're counting. Okay? Just be in the day. It's like, okay, this is about how much time you have left. Yeah, normally a term is 9 weeks, but this one is 10. Her head's going to slide off her shoulders in just a second. All right.
Break like 3 days.
You get Friday and Monday. All right. So today we're going to talk about cross sections. So a cross section of a three-dimensional solid that is an object that has both length, width, and height is the figure obtained when the cross section is intersected or sliced by a plane. An object that only has length and width like a flat sheet of paper. Or, I'm curious, I think that this is a toy that has become less popular over time. Did you guys ever play with the Play-Doh Fun Factory when you were a kid? Where you could put the Play-Doh in the deal and you had different things and you could, you basically it squirted out through the deal. And then you, at some point, you, so you could cut that off. You didn't have to use all of the Play-Doh that was in there. You could cut it at one point, put it in a deal, and cut it. So when you cut it, the surface from that cut is the cross section. Okay? So we're going to look at shapes that can be created by slicing various types of solids. So part of the reason I did this in color is because I think it just is easier to see a little bit if it's not all gray. So the diagram at the right shows a sphere, like a solid ball, like a pool ball, for example. Not like a tennis ball. Sorry, the crows were chasing the hawk. It was kind of fun to watch. So not like a tennis ball that is not solid all the way through. Okay? So the cross section is the part of the sphere that is touching the plane. What is the cross section here? Well, if you were to actually, have something that could cut through a pool ball, and then you picked it up and looked at the part where it was cut, what would that cut make?
Circle.
A circle. If we were to cut the sphere higher up, but still cut horizontally, so we're not going to change the angle, but we just moved it up a little bit more, how would the new cross section be different from the first? What would be the same? It'd be smaller,
But it would still be a circle.
but it would still be a circle, exactly right. So, is it possible for the cross sections of a sphere to be any shape other than a circle?
No,
Why or why not?
because it's a circle all the way around, so it has to be a circle.
It's difficult to explain this.
Circle all the way around, but it has to be a circle.
It's a circle all the way around.
So it has to be a circle.
So I agree with you, no.
It's a circle, so it has to be a circle. There's no other plane for it to
Yeah, if I change the angle, would it change the cross section?
No.
No, it's still going to be a circle. The angle, or I'll call it the level of the intersection, meaning how far it is from the center, can only change the size, not the shape. And actually, the whole reason we're doing this is so that we can talk about volume. Thank you. All right, so Carlos wonders how the cross-section of a cylinder would look. So he's drawn a picture of a plane intersecting a cylinder where the plane is parallel to the two bases. Remember that the bases of a cylinder are those two circles that are parallel to each other and are congruent to each other. So what shape is his cross-section here? Still a circle. If he were to cut the cylinder higher up, but still parallel to the bases, and this should be cross-section, not course, would the cross-section be different, as in problem 1, or the same?
Like that? Or like
Still horizontal.
Like same.
Yeah. Would the size change here?
No.
No. Every cross-section parallel to the bases would be the same size circle. Okay, now, instead of cutting it parallel to the two bases, what if we cut it perpendicular to the two bases? In other words, we're cutting from top to bottom now. What kind of a shape would this be? Talk it over with the people around you. I don't want just one or two people answering the question. What do you think that shape would be? Talk about it.
So rectangle. No, I swear it's actually a rectangle. It's a rectangle. No, dude, usually it's covered in like.
All right. I'd be happy to hear any. In my group, we talked about it being this. Yes, Johnny.
Rectangles.
Yeah, they would all be rectangles. And are they all going to be exactly the same shape? Are they all the same size? No. Now, are they all going to be the same height? Yes, but as you get further from the center, they're going to be less wide, right? They'd be all the same height. but different widths. Now, if you cut through the center of the circle, no matter how you did that, they'd all be the same size. But if you moved away from the center, they get smaller. So is there any cross-section that we can make with a cylinder and a plane that would be different from the shapes in part A and C? If so, how? And if not, why not? Talk it over with the people around you for just a minute or two.
Cut a diagonal.
No, like if you cut it, that would look like the top portion, not like the side. Yeah.
No, because you would have to stretch. It'd be like a stretch circle. We'd be cutting this out.
All right, I'd like to hear some ideas. By the way, the answer is to the first question is yes. The answer to the second question gets more interesting. So, Ben, I heard you talking about something. Tell me what you were talking about. Oh, no. Front Ben. All right, so diagonally so that it just went through the sides? So you're talking about cutting it like this?
Yes.
What kind of a shape do you think you would get that way? Yeah, you get something that's, and it depends on what you mean by oval. Different people have different, in math, that's called an ellipse. You may have talked about in science that the orbits of the planets around the sun is not a circle, it's an ellipse. Have you guys never talked about that? I've got to have to talk with your science teachers. You should talk about that. It's not a circle, it's an ellipse. Now, it's close to a circle in most cases, except for the planets that are much further out. The nearer planets, it's pretty close to a circle. How else could you cut this so that you wouldn't get either a rectangle or a circle or an oval? Yeah.
By not cutting.
Okay, that wasn't an option. Thank you, though. Well, let's take a look on back. And this verifies exactly what Ben was talking about. If you do this at an angle so that it doesn't go through either of the bases, but it's not parallel to the base, you get this ellipse. Well, so oval is not really a mathematically well-defined word. An ellipse is. Oval, so for example, there are some people who say, like, if you look at the track around a football field, they'll say that that's an oval. And I'm like, okay, it doesn't look very oval to me, but, you know. That's not an ellipse because it's got straight sides. Okay? But an ellipse actually has a mathematical definition. And an oval, I don't think does. The other thing you could do, it occurs to me, is what if you cut it, and I'm not going to draw this, but what if you cut it like that? you're going to have, there's going to be a part that's going to be straight, and it's going to be kind of like, sort of like a doorstop, but weird on one end. I mean, it's going to be an odd looking thing. All right. So before the break, we learned that the volume of a solid is determined by the number of cubes it takes to create the solid. We did that, right? Everybody remembers this, yes?
In theory.
In theory. So, a prism is shown at right in which the length of each edge of each cube is 1 inch. How can we slice the figure so that every cross-section is the same? So if I slice this vertically, would every cross-section be the same? If I sliced it here, is that going to be the same as if I sliced it here? No, those are going to be different. How could I slice it so that every cross-section is going to be the same? Yeah, slice horizontally. Now, this is how we're going to put this together with the idea of volume, so you need to pay close attention to this. So if we slice the figure in part A and traced it on your paper, what would the area of the cross-section be? So if we just looked at the cross-section, it would look like this. So what would the area of this be? Yeah, the area is going to be 8 what? It's going to be 8 square inches. Part C, how many cubes are in the bottom layer of the prism?
8.
There's 8. Do you notice that that's the same as what we got here? Yeah. They are the same. That's a super important idea for us, is that the area of the base is equal to the number of cubes that occupy the base. Right? Now, how many layers are there from top to bottom? There's 2 layers. So how can we use our answers from part A and part B to find the volume? Well, the volume then is going to be every layer has 8 cubes in it, and there's 2 layers. It would be 16 cubic inches. So if we know how many cubes are in the base, and then we multiply by how many layers there are, we will get the volume. That's an idea that you use over and over again when you're doing volume problems. And the number of cubes on the bottom is equal to the area of the bottom. So, let's use these ideas to find the volume of these different prisms. So for this one, how many cubes are there on bottom? 6. And how many layers deep is it? 2. So that's 12 cubic inches. This one, it didn't draw all of it, but we know that this is going to be 6, and that's going to be 9, and that's going to be 6. What is the area of the bottom going to be here? 54, because it's 9 times 6. Times, how many layers would you have? You'd have 8 layers. See, that's 400 plus another 32 is 432. We'll assume that these were in inches, cubic inches. Now, this one is a little bit different for two reasons. The first reason is that the bases aren't on bottom. Because if I sliced horizontally here, would every layer be the same size? No, they get smaller as you get towards the top. So here, the base is this triangle. If I sliced it from front to back, vertically, would every slice be the same? Yeah. So, let's find the area of the base. The base area, it's a triangle. How do you find the area of a triangle?
Base times height divided by 2.
Okay.
Half of base times.
Or half of base times height. Either way you want to do it is fine. So that's going to be 16 times 7 over 2 is 56 square centimeters. And then how many layers would you have from the front all the way to the back? There's going to be 20 of them. So the volume is going to be 56 times 20, which is 1,120 cubic centimeters. So if we know the area of the base, we can just multiply that by how far apart the bases are to get the volume. That's a big important idea.